Hello student, today let us solve this given LPP by simplex method. Now this is a minimization problem. So first of all you have to convert it to a maximization by using the dual property. So now the original problem is this one, minimize set is equal to this subject to this constraint, where we have the second constraint is less or equal type, not of greater or equal. So first of all, before we convert it to the dual problem, then we need to convert first this one to greater or equal, since it is a minimization problem. So for that one, the given LPP can be written as the objective function will remain as it is subject to the constraint. The first constraint will remain as it is. The second constraint now will become, in order to convert it to greater or equal, you have to multiply on both sides by minus sign. So it will become minus x1 minus x2 minus 2x3 greater or equal to minus 8, and the last one will remain as it is, equal to 2. So now here we can have this matrix representation of this one. The matrix representation of this given LPP now can be written as, where the first column will represent the coefficient of x1, the second one will represent the coefficient of x2, and so on. So let us see what will be the coefficient of x1. It will be 1 minus 1, and 0 is absent in this third equation, so it will be 0, and we have 1 as a coefficient of x1 in the objective function. So you have to write here 1. The second column will be the coefficient of x2. It will be minus 1 minus 1 minus 1. It is plus 1 here. The coefficient of x2, it is 1 here. And then what is the coefficient of x2 in the objective function? It is 2. So you have to write 2 here. The next one will be the coefficient of x3. It is 1 minus 2 minus 1, 1 minus 2 minus 1. And the coefficient of x3 in the objective function is 3. Now what is the last one? Last one will represent the value of the equation in the constraint. So it will be 4 minus 8, 2, and then let us put a star mark for this last one. So this is the matrix representation of the given LPP, where we have already converted this greater or equal sign in the constraint to, the less or equal sign in the constraint to greater or equal sign. So now after this, what you need to do is find the transpose of this one. So if you find the transpose of this one, so the first column or the first row will become the first column. So it will be 1 minus 1, 1, 4. The second row will become the second column. So it will be minus 1, minus 1, minus 2, and then minus 8. The third row will become the third column. So it will be 0, 1, minus 1, 2. And the last row will become the last column, 1, 2, 3, star. So what will be the dual of this one using this matrix? So the dual of this problem is maximize now. F is equal to, this will be give you the objective function. 4w1 will take another variable minus the 8w2 plus 2w3. Subject to, what will be the first constraint? This one will represent the first constraint. So it will be w1 minus w2 less or equal. Now it will become less or equal to 1. Then minus w1 minus w2 plus w3 is less or equal to 2. The third constraint will be w1 minus 2w2 minus w3 less or equal to 3, where all wi are greater or equal to 0. So we have converted the given LPP into a maximization problem before we solve it by the simplex method. Always remember that to solve the given LPP by simplex method, you need to make sure that the given LPP should be a maximization problem. If it is a minimization problem, then in that case you have to convert it to the maximization problem by using the dual property. Like in this case, what we notice is that the given LPP is a minimization problem, but we have one of the constraint to be the inequality in one of the constraint to be less or equal, but we need to convert this one to greater or equal before we find the maximization problem using the dual property. So always, if there is a less or equal inequality in the constraint of a minimization problem, first you need to convert that one to greater or equal. Now after this, let us form the initial. So we can next introduce, now you see that before we write the initial simplex table, so let us introduce the slack variables here, because this one is less equal to 1, less equal to 2, less equal to 3. So we have to introduce the slack variables in all the constraint in this case. So for this one, let us introduce W4, for this one W5, and for this one W6. Therefore, therefore the dual problem will have the objective function now as maximize f is equal to 4w1 minus 8w2 plus 2w2 plus 0. Here in the objective function, we have to write the coefficient of w4, w5, w6 as 0. Now subject to the constraint. So in the first constraint, we introduce the slack variable w4. So we have to write the coefficient of w4 in the first constraint as 1, the rest as 0. So this will be equal to 1. In the second constraint, we introduced the slack variable w5. So the coefficient of w5 should be 1, but the coefficient of w4 and w6 should be 0. And this will be equal to 2. And in the last one, we introduced the slack variable w6. So the coefficient of this will be 1, and then the rest will be 0. So this is equal to 3, where all the wi are greater equal to 0. Now we can form the initial simplex table after converting all the inequality sign in the constraint to equal sign by introducing the slack variables. So what will be the coefficient of non-slack variables? The non-slack variables in this case are the coefficient of W1, W2, or the coefficient of non-slack variables are the coefficient of W1, W2 and W3. So the first one will be 1 here, W2 is minus 1, and since W3 is absent from here, so it will be 0. Next one will be the coefficient of W1 is minus 1, minus 1, 1. And then next the coefficient of W1, W2, W3, it is 1 minus 2 minus 1. And then what is the coefficient of W1, W2, W3? This is W3. In the objective function, it is 4 minus 8, 2. But we have to write the negative of this one. So it will become minus 4. Then minus of minus 8 will become plus. Then this will be minus 2. The coefficient of slack variables, you can see that is the coefficient of W4, W5, W6. So the first row you'll have 1, 0, 0. The second row you'll have 0, 1, 0, 0, 1, 0. And in the third one you'll have it as 0, 0, 1. Now here it will give you, this column will give you the value of the coefficient equations, that is 1, 2, 3. So it will be 1, 2, 3. The last row here in the coefficient of slack variables should be 0 everywhere, and this is 0, the value of the equation at the origin. So now this is the initial simplex table. Now from this initial simplex table, what we need to do, we have to eliminate the negative indicators. That means we have to convert all these negative indicators in the last row to either the 0 value or the positive value. So in this case, let us select, since we have in the first column, these are called the negative indicators. Now in this case, we have two negative indicators, one that belong to the first column and another one belong to the third column. So let us select this one. You can also select this third one also, doesn't matter, you'll get the answer will be the same only at the end. But in this case, let me select this one, minus 4 as negative indicator here. Then from this one, what we need to do now, you divide the value of this equation by the coefficient of this W1 or by the corresponding entries of this one, the first column, that is the column that belong to P1. Now here for the first one, what will be the quotient? 1, if you divide it by 1 by 1, it gives you 1. Now since minus is this, since we have minus 1 here, then we ignore that one, because if there is a negative entry in that column of the coefficient of non-slack variables, then in that case we need not divide the value of the equation by that entry. And then the next one will be this one, 3 divided by 1, which is equal to 3. Now this is the smallest one, the smallest quotient. Then you select this one. So this will be the pivot entry. So you name it as P1. So you'll see that here we can write in the next one as 1 minus 1, 0. This is the pivot entry. Since it belongs to the first column, so we have to label this row also as P1. So this will be minus 1, minus 1, 1, 1 minus 2, minus 1, the minus 4, 8, minus 2. Then this is 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, then 1, 2, 3. So this is the pivot entry. Now next what we need to do is, since the pivot entry is already 1, so we need not convert it to 1 anymore by the row operation. But now we need to convert all the entries below this pivot entry, that is this one, and this to 0. So for that we have to use a suitable row operation. So for R2, to convert this -1 to 0, since it belongs to the second row, so apply this row operation. R2 is equal to R2 plus R1, and then to convert this one this one also to 0, now you apply this row operation for the third row as R3 minus R1, the first row, and the last one is this one R4, the fourth row. In order to convert this -4 to 0, you apply this one R4 plus 4 times of R1. So after applying this row operation here, then we can have the entries of the next simplex table as this P1, P2, P1 will remain as it is. So it will become 1, -1, 0, 1, 0, 0, 1. The first row will remain as it is. Now the second row will change. 1 minus R2 plus R1. So -1 plus 1, it will become 0. -1, -1, it will give you -2. Then 1 plus 0, it will be 1 only. Then next, it will be 1 minus this, it will become 0. -2 minus of -1, so this will become plus. So -2 plus 1, it will give you -1. Then -1 plus 0, -0, it will be, -1. Here in this case, -1 plus 0, it will be -1 only. Now next, what will be the value in this case? 0 plus 1, it will be 1. Then 1 plus 0, it will be 1. 0 plus 0, it will be 0. The third one now, it is R3. We apply the row operation for that third one, R3 minus R1. So that means 0, 0 minus 0, 0 minus 1, it will become -1. Then 0 minus 0, it will be 0. 1 minus 0, it will be 0. Then here it will be 2 plus 1, it will become 3. And then this one, it will be R3 minus R1. So that means 3 minus 1, so it will become 2. And what about the last row? It will be -4 using this operation R4 plus 4 times of R1. So -4 plus 4 times of 1, it will become 0. 8 plus -4 of -1. So in that case, it will be 8 minus 4, that will become 4. -2 plus 4 times of 0, that will be 0. So it will remain as -2. Then 0 plus 4 times of 1 here, it will become 4. 0 plus 4 times of 0, it will be 0. 0 plus 4 times of 0, it will be 0. And the last one, the initial value is 0 here. But 0 plus 4 times of that one gives you 4. So this is the next simplex table after applying the suitable row operation. R2 to be R2 plus R1. For R3 it is R3 minus R1, and for R4 it is R4 plus 4R1. Now since we still have a negative indicator, so let us like this one. So what we need to do now, find the quotient here. You divide the value of the equation here by the corresponding entry of this third column, since this -2 belong to the third column. So if it is if you have the 0 entry, that one also has to be ignored. Now next you divide 3 by 1. 3 by 1, it gives you 3. Then 2 divided by -1. This also we have to ignore because the entry here is negative. So that means there is only one quotient here, in this case 3, and that one will be the smallest quotient. So we select this one and see that this will be the next pivot entry. So you denote here as P3 since it belongs to the third column. So now what we have to do, since again in this case, since one is already the entry of the pivot, therefore we just have to convert the entry now above this pivot entry also, it is already 0. So we need to convert the entries below the pivot, that is below this one here, to 0. That is -1 to 0 and -2 to 0 by this following suitable row operation. So you can apply this one for R3, that is for this one it will be R3 plus R2, because this is -1, this is plus, so when you add it, then you'll get 0. And for this one, R4, you apply the row operation, R4 plus 2 times of R2. So it will be plus 2 times of R4. Sorry, R2. Then after applying this row operation, okay, this P1, the first row will remain as it is since there is no change for this one. The second row also, that is P3, 0 minus 2, 1 also will remain as it is, 1, 1, 0, 3. Now this row, the third row and the fourth row will change after applying this row operation. 0 plus 0, this one, 0 plus this one, it will be 0. Now minus 1 plus with minus 2, so we'll get minus 3 here. Minus 1 plus 1 here, it will become 0. Minus 1 plus 1, it will give you 0. 0 plus 1, it will become 1. Then 0, okay, this one is 1 here, the original value. So 1 plus 0, it will be 1 only. Now 2 plus 3, it will give you 5. And the last row, you apply this operation, R4 plus 2 times of R2. So 0 plus 2 times of 0, it will be 0. 4 plus 2 times of minus 2, then it will become minus 4. Plus with 4 becomes 0. Minus 2 plus 2 times of 1 here, then it will become 0. 4 plus 2 times of this, it will become 6. 0 plus 2 times of this will give you 2. 0 plus 2 times of 0, this will be 0. Now here we have 4. Now 4 plus 2 times of 3. 2 times of 3 will be 6. 6 plus 4 will become 10. Now what we notice is that this simplex table here has no more negative indicators in the last row. So therefore this will be the terminal simplex table. And the value of that objective function will be given by this 10, which is this one. Okay. So now to check that what will be the value of the original problem and what will be the value of those wi for the dual problem. So what you have to do now, this one will represent you that x1 and this one will represent x3. Since there is no labeling here for this P2, it means that the value of x2 should be 0. x2 should be 0. So therefore for the optimum solution will be x1, this will be for the maximization problem. So the optimum solution will be x1 is equal to 1, not x1, this will be w1, w3, and this is w2. w2 is equal to 0. This since this simplex table is for that dual problem, so the optimum solution for the dual problem will be w1 will be equal to 1, w2 is equal to 0, and w3 is equal to 3. w3 is equal to 0. Now if you substitute it in that equation, if you substitute the objective function here, w1 is equal to w1 is equal to 1, w2 is equal to 0, and w3 is equal to 3. w3 is equal to 3. Then in that case, you'll see that 4 into 1 minus 8 into 0 plus 2 into 3. Let us calculate. It will be 4 into 1 will be 4. This will be 0 plus 6. So it gives you 10, which is exactly equal to the value of this one, the objective function here. So therefore for the optimum solution for the dual problem will be w1 is equal to 1, w2 will be 0, and w3 is equal to 3. And for the original problem you have to see from here. And for the original problem which has the variables in terms of x1, that is this one, x1 plus 2, x2 plus x3. So here this 1 will give you that q1, this is q2, this is q3, which means that x1 is equal to 6, x2 is equal to 2, x3 is equal to 0. Let us verify that by substituting the value of x1 is equal to 6, x2 is equal to 2, and x3 is equal to 0, whether we are getting the same value as 10 or not in the original problem. So we have here minimized set is equal to x1 plus 2x2 plus 3x3. So what is x1? I have it as 6. So this is 6 plus 2 times into 0, 2 times into 2. And what is x3? It is equal to 0 plus 3 into 0. Now 6 plus 2 into 2, it will be 4. 6 plus 4 gives you 10. So the value will become 10, which is exactly this one. Therefore, the optimum solution for the dual problem will be given by the value of this one, W1, that is P1 equal to 1. W3 will be, because we mark it as P3, that means the value of W3 will be equal to P3, which is 3. And since there is no P2 here on this side, so it means that the value of W2 should be 0. Now to get the optimum solution for the original problem, you have to select the value from this last row which belong to the coefficient of the slack variables. So Q1 here means represent that x1 which is equal to 6, Q2 here represent that x2 which is equal to 2, and x3 here is equal to Q3 which is 0. And when you substitute it in the original problem, you will get exactly the value 10 in this case, which is the value of the objective function for both the original problem and the dual problem. Hope it is clear now how to solve the given LPP if the given LPP is a minimization problem. So you have to convert it first to a maximization problem, and then after that we can use the apply the row operation in order to get the required solution of the dual problem and at the same time of the original problem.